Oh, okay, right. I thought we were 2 minutes early, but welcome everyone to the second last slot of the day, to this session about high performance computing. Who thought that this title is a bit of marketing, honestly? You're hesitating, you say yes. It's not marketing. To answer the question that you didn't even ask first, we had at least 2 customers that I can talk of that were using more than 1 million cores in the cloud. Western Digital was one of them. They use Docker images. Those Docker images, they are stored on ECR, on the container registry in AWS, and they use the service called AWS Patch. And they use this service to orchestrate their workloads. It was a single cluster with 1 million cores, and they leverage spot instances, which is maybe the coolest part of the story because this gives you a price discount of roughly 80%. And their computations, their simulations that they were running, they went down from a total of 3 weeks to 8 hours. Another customer, they used 1.1 million virtual CPUs for machine learning, for natural language processing and generation of topics. So it's not marketing, it's happening basically every day. You could start doing this this afternoon. And if you think about using 1 million cores, what would you could use it for? Now I spent like 4, almost 5 years of my career in high performance computing. And when I started my first job, it looked like this. Probably when you start your first job, somebody's telling you, look, we have this web application and can you make it run faster? When I started, I was working in a university hospital and my boss showed me this and he said, you know, that's the data that we need to process. We have patients, we have existing algorithms, but before we have finished calculating images up with these existing algorithms, the patients might be dead if things go wrong. So what they wanted to do is this. This was like the outcome of working 4 years and trying to speed up this, this lot of steps of existing algorithms. So what you see here, those red areas is where you feel pleasure actually, and where you also feel pain. This is where your opioid receptors are, and that was the outcome of a long project. Now, when I was working there was no high-performance computer. I actually went to a data center where they had a high-performance computer, and I said, "Look, we have this application, and can I use your high-performance computer?" And they said no, because they didn't know me, and I was a student at that time. So, one question is, how can you speed up things that take hours? Here, all the processing steps at the beginning, they took several days. How can you speed up such things? And there is a secret. I'm not supposed to tell you because usually we keep it inside of the high-performance computing community. But there's the secret, which is basically you take 18 months or 2 years off and you go surfing. And then if you come back and you remember Amdahl's law, the processing power has doubled, and then you have a speed up of 2, which is actually a very good speed up. And to get a speed up of 2 using, other things, better algorithms, better hardware, it will probably cost you a lot of time and money. So having such a speed up of 2 would be fantastic, but as you can tell, it's a joke. Now, it never worked. It never worked so far, I tell you. It never worked because if you buy such a high-performance computer, well, you don't really buy it. You rent it or you lease it for 4 years, and then you have it for 4 years. But it's a fixed-size computer that is probably like, the size of this room times 3. That's the one that I have seen personally. And you have it for 4 years. So if you go surfing for 2 years and you come back, nothing has improved now. And it's also fixed size. If you need to run a set of different variations of permutations of your parameters, you can only do it sequentially. And the other thing is, you will invest like, tens of millions of dollars for buying such a computer. So the whole thing of, going surfing and coming back is not really working out at the end. Well, so far. Because, when I was doing this project with those brain images, I was kind of ready, just to pay for my computation time, but they wouldn't even accept me at this high-performance computing center. They said, no, like basically go away. If you want to be accepted for such an environment, you have to write a narrative, you have to talk to a committee, and then they will decide if they want your workloads or not. And one thing to understand is that those high-performance computers, they're always full. They always run at full capacity. And the reason is that all these applications that those people run, like climate research, they use grids or they use cubes. And if they have more compute resources, what they do is they just make the size of the grid smaller, and this is when you have to the power of 2 or power of 3 more compute requirements. And the other thing is capacity. That's what I told you. It's always running at full capacity, and the technology is like fixed for 4 years. This is why this joke is not working out. But it's working out if you go to the cloud now. So if you do what Western Digital did, if you come with your workload to the cloud, you just pay for what you use. And when I was a student, I was willing to pay for it, but I just couldn't. They wouldn't even take my money. And the capacity is not fixed anymore. And this is what I want to show you here. So for a classical HPC environment, it looks like this. Almost a bit like a Tetris game, isn't it? Because you have to fill those empty gaps to make it worthwhile. If you don't fill those empty gaps, at the end of a year, there will be some report telling you, that you didn't fully use your high-performance computer. And this is how it looks in the cloud now, where you can stack things on top of each other, where you can have dynamic capacity. Now, some of you using AWS might remember that there is a limit that you have. It's a soft limit, but you can always increase the soft limit. The soft limit is basically there, well, for 2 reasons. First of all, to protect you, not to do stupid things when you start, and second, for us to give us some idea of capacity planning. But if you want, you send us an email or you raise it. There is a service now for those limits. You raise those limits and you ask, for 1,000 or 10,000 or 100,000 or even 1 million vCPUs, and you will get them. So what I want to cover in this presentation is basically a couple of things that we need and that make the AWS cloud special for high-performance computing. And at the core, certainly, there is compute. So I want to briefly tell you a little bit about special EC2 instances that make a lot of sense for high-performance computing. Then there is storage. We need storage, and there is special file systems that we can use in HPC. And then we have networking, and I try to convince you that networking is the most crucial part, and that makes a big difference of your home-built Linux cluster. And actually, I had to build my own Linux cluster to process those brain images because I didn't have any other solution. So the networking is a core part. Then automation, orchestration, we will come to this, and visualization. I'm not talking a lot about visualization here in this talk. So if you go to AWS now, and if you select an instance size, maybe the T2 micro that you know because it's incredibly cheap. There is 190 other instance sizes that you can select from, and that's actually quite interesting because you can pick any of those instance sizes and build a high-performance computer out of it. And that's very interesting because remember, if you buy such a HPC machine, you have a fixed size machine with a fixed size of processors and a special kind of processors that you cannot change. So if you look around what's happening in academia, there's lots of students working on such problems, and what they do is they try to optimize the way they process certain things. They try to optimize algorithms for a special high-performance computing machine. Now think about this. Does it make a lot of sense? Couldn't it be the other round, that you just pick the right hardware, you pick the optimized hardware, and then make your algorithm run on this hardware? So we believe it should be the other way around, and this is why you have this wide choice of 190 different instances. And because we have so many, they might be a little bit confusing. I want to give you, well, some explanation about the way we name them. So it's like P3DN24X large, and I was trying to color code this. The P, it's the instance family. So P basically for GPU, it's a general purpose GPU instance. The 3, That's like the version number now. It means like there was a version 2 and there was a version 1 before. And then the D and the N, we like to call this capabilities, like D for disk and N for network. Basically, the D for disk says there's an NVMe-based SSD behind it, which is a local, very fast SSD. And the N for network says there is 100 gigabit per second networking available. And as I said, I will come back to this networking later. And then it's the instance size, the 24x large, that is used here. So let's look at like 3-4 different instance types quickly, because I think it's quite interesting to see what we offer here. So the P3DN is basically what I explained you already. It's a GPU-based instance that comes with a fast disk. This is why we have the D, and with 100 gigabit networking. This is why the N is in the name. And all those GPU-based instances, they're very popular for machine learning, because the GPUs bring you a lot of cores, and those cores, they bring you concurrency, they bring you parallelism, and in these instances we have 8 NVIDIA GPU Tesla cards. There is 96 custom Intel Xeon processors, and as I already told you, the networking and the storage. And then there's something special which is called EFA, the Elastic Fabric Adapter. And this is basically what puts us in the networking, in the HPC class networking. And I will talk about this later. Another instance type, very different, but also very popular, is called Z or Z1D. And it's a high clock speed. It's 4 gigahertz. And it's a 4 gigahertz sustained clock speed. So it's not what my PC or my laptop does, where you have this boost, where it's trying to save as much power as possible and try not to produce that much heat. This is a constant high clock speed, and it's a relatively low number of processors. And the question is, why would you want to have this? No, doesn't it make sense? I was talking about millions of cores. Doesn't it make sense to have as many cores in a CPU as possible? This goes the other way around. So, yeah, why? Why would you have a few cores that give you constant high clock speed? The answer is this is more for traditional software, like the traditional database vendors, where you pay per core. And this is why customers ask us for such instances. C5N, C, well, just remember C for compute, N for the networking, that's the capability. That's a very fast compute instance. The N gives the high bandwidth for the compute instances, and it's massively scalable performance. So if you have any problem that you can crack with this is the right instance size. Now, so far, a lot of people thought high-performance computing is like having the newest and fastest Intel processor. And what we did, well, beginning last year, is offering you AMD processors as well. Now, AMD, you might remember them from your PCs that you built at home. They're binary compatible. So the software that you can run on Intel processors, you can also run them on AMD processors. And if you look at those instance types here, like there is for the M5, we got an M5A with an AMD processor. For the R5, we got an R5A, and for the T3, we got a T3A. Why would you want to do this? Because it gives you like a 10% saving, which is a lot of money if you spend hundreds of thousands. So these are relatively, well, it's quick to change because there's this instant size compatibility, and there's this binary compatibility that probably every program that you can run on your Intel processors, you can also run on the AMD processors. And then we have something that is, I think, actually quite much more exciting. And it's not the A as a capability, it's called A1. So it's a different instance type. And this A1 instance type is a Graviton processor. It's a ARM processor, ARM. Now, do you know the ARM processors? These are the processors that you have in your mobile phone. These are the processors that you find on those small compute boards, no? to play with. But so far, these weren't the processes that you would expect in server-class machines. But now they're there. And we think right now is the time to use them in server-class machines. The question is why? And the answer is because for the same performance, you get like 45% of discount in what you need to pay for this performance. Now, those ARM processors, if you ever tried them on a Raspberry Pi maybe, they're not binary compatible. You couldn't even run a normal Linux Docker container that is compiled for Intel on these ARM processors. So why am I advocating them? The answer is they make a lot of sense if you're not trying to run, software that comes from SAP or Oracle. But if you're trying to run your own microservices and if you want to scale out your microservices, and if you then get a 45%, in price reduction, that's a lot of money. And typically those microservices, it's your software that you built yourself. So you compile it yourself, and then they will work on the ARM processor. Remember when I talked about this first instance type, I mentioned this EFA, the Elastic Fabric Adapter. And the Elastic Fabric Adapter is it's a super cool story in my opinion, because this makes a real difference between, getting a bunch of Linux PCs and putting them together with a 100 gigabit network switch or having a real supercomputer. Now the difference is it's about latency. It's all about latency. If you think about networking, I told you about this N for networking, this extra capability that we have where you get 100 gigabit per second networking. Now go and tell this to the high performance computing people. They say, yeah, that's nice, we need to load in a lot of data sometimes, but they're not crazy about it. Fact is that you can increase the bandwidth for networking very easily. You put in a second network card, you use a second cable, and you double the bandwidth. Now, everyone can do it almost. But to decrease the latency, like the time that you need to send 1 byte or 0 bytes, just the latency to get from one core to the other core, that's incredibly hard to decrease this. And the more you decrease it, the more you get to limits that you can't easily remove. Do you know what the typical network latencies are for a TCP/IP-based network? Anyone? Any guess? Yeah, they're typically like milliseconds, so like 10 milliseconds is okay. We tend to say it's like a single-digit millisecond. But to decrease this even further, it's incredibly hard. And you will realize that the TCP/IP stack itself is one of the problems now. And people think they can't get away, they can't take away this TCP/IP stack. And the other thing, obviously, is the hardware. You need good hardware to support low latency networks. And this EFA, this Electric Fabric Adapter, is such a hardware. So it's HPC Cars Networking. That brings you in the region of 50 microseconds. So it's from a single-digit millisecond to 50 microseconds. And this extra capability, it's available for the C5, for the P3, and for the E3 instances. And it's a separate network card. And it's also bypassing the TCP/IP stack. And that's the interesting thing that happens. Now, you might think, what do you have left if you get rid of the TCP/IP stack? Your Chrome browser will not working anymore because it's HTTP on top of TCP/IP. The answer is, well, it's built for high-performance application. It's built for special build programs that want to have the best performance possible and that want to have the smallest latencies in the networking. So what happens is those applications, and I'm trying to show you one later, they're very often using a library called MPI. It stands for Message Passing Interface. And this MPI is kind of what you know from JMS or Kafka. It's sending messages, basically. So those nodes that run in parallel, they use MPI to communicate with each other, to send data, to send control information. And a lot of the applications that you see in the HPC space, even when I did this like many years ago, they're written based on MPI. So if you have MPI, Typically what you do, MPI is running in user space. It goes through this TCP/IP stack. It goes to the network card. But what we do now is we take MPI, we have a special library, it's called LipFabric, and the LipFabric directly talks to the EFA device, to this elastic fabric adapter. And this is how we bypass the TCP/I kernel, which is fine, and we still have the classic network card if you need to do TCP/IP-based networking. And this is the way, to get rid of the latencies that we get here. Also, if you try to lower the latencies, the jitter starts to be more noticeable. And this is the way to avoid this. Right, so that was the networking part. And then we have something, also purpose-built file system for high-performance computing. So what I'm trying to do is trying to explain you that it's not a bunch of instance types that you just put together that use a normal networking and a normal file system, but it's purpose-built instance types, which is super performant, and then the low latency network, and then we have this parallel file system. It's called FSX Lustre, and I think the majority of all top 100 supercomputing machines, there is a list, there is a hit list of those top 100 machines, they're using FSX Lustre. So it's a special purpose-built file system. It's open source. It's a word that is kind of put together from Linux and cluster. This is where it comes from, Lustre, Linux and cluster. And it's based on SSDs. As you see here, it's a parallel file system. That means I/O happens in parallel. Of course, it seems like one unique file system to you, but I/O happens in parallel. It scales very well. So if you add more data, you get more throughput. And this is why a lot of people like to use it. So it scales very well, and it gives you guaranteed throughput and a very low latency throughput. And if you remember that we are using a lot of S3. S3 is the key value or the object store that we have in the AWS cloud. And basically, a lot of data is stored in S3, even for big data. And so the FSX can be initialized using a S3 bucket. And it's then using the data in FSX in this low latency mode. And then once you're finished, you can write back your data to the S3 bucket. And FSX Lustre, as I said, is one of the most popular file systems that exists in the high-performance computing world. Right, and then there is something newish. It's not completely new, but I want to mention it here, and I want to show you this also later. It's called Parallel Cluster, and it's an open source project. It's an open source project based on Python. You can simply install it if you go to, if you have pip, and you can basically pip install it, pip install Parallel Cluster. And what you get is a environment that allows you to set up your own high-performance computer on top of AWS. It used to be there before. It was called CFN cluster, and people liked it a lot. This is why we put a bit more, resources behind, a bit more engineering behind. It got a different name. It's called Parallel Cluster now. And at the end, what you get is a command line shell, and you can say p-cluster, and you can create your own high-performance computing cluster. You can use the elastic fabric adapter. You can use spot instances like what they did at Western Digital when they were running their simulations with over 1 million cores. You can have, you have schedulers pre-installed. If you work in an HPC environment, you're used to submit your jobs to a queuing system that is then processing those jobs in the best suitable way, and those schedulers, they're pre-installed. You can choose from 3 of them. And as I said, it's open source. So it's this is the URL, and you can get it from there, install it with pip. I'm trying to show you this. Let's see. And basically not this. Let's go here. Okay. So this is my local machine. That's important to understand. So if I say clear here and I say p-cluster like list, it will say, there is pcluster already installed, so I did this pip install already. And I have a cluster already configured, which is called HPC Tool. But I could say pcluster configure, and then configure, well, the settings for a new high-performance computing cluster. And, well, it says which template do you want to use. I say default. Then it says what region do you want to run in. Remember, we have like 22 different regions in the whole world. I think those regions consist of 69 different availability zones. So basically every region has at least 2. Usually the newer regions, they have 3 availability zones. So I like Ireland, so I go for EU West 1. The VPC name, it should be public. The key, I need a key to talk to, well, to the master node in this HPC cluster. And I have it already, well, I created it already, and I uploaded it already to the Ireland region. This is why I have to stick to the name. It's called pcluster key. And the VPC that I want to use is this one. I only have one. Then I need a subnet ID for the master node. Doesn't really matter. I take the one that it's suggesting here. And what it's doing now, it's creating a config file. And based on this config file, I can instantiate a HPC machine. And this config file is actually here. It's under .parallel cluster config, and it looks like this. So basically, you see what we were doing before. So it's using this key. It's the VPC setting. There are some additional parameters that I put in here. Like it says initial queue size. When it starts up, there should be 2 machines already in the cluster. And, well, to not spend too much money, I want a maximum of 4 machines. And the machine type for the compute instances, it's specified here. It's the C5, remember C for compute, and the 18X large. I think these are the ones with 72 cores, and it's, because they do hyper-threading, it will be 72 times 2, 144, if I'm right, virtual CPUs. And then I have a master node that is kind of, you know, running the queuing system and doing all the orchestration. For the master node, I'm happy with a general purpose instance, which is the M5 X large. And, well, these are all the settings that I basically just configured. Now, what I normally would do is a pcluster update to send those new settings to the existing cluster. Because it's there already, I don't need to do this. And what happens behind the scenes, behind the curtains, is it's generating CloudFormation, which is the standard way of doing infrastructure as code. And it's running the CloudFormation, and it's using the CloudFormation, you know, to set up the compute instances. And what I can say now is pcluster start HPC Tool. And it is actually there already. It is running, but it shuts down itself in a time that I define here. So after 240 minutes, it will shut down. This is when those compute, oops, what is this? Okay, this is when those compute instances will go away. Right. Okay, so this looks good. Now I want to connect to the master node. And to connect to the master node, what I do is, I'm connected here already, but let's do this again for you. Basically what I do is I say pcluster SSH to the HPC Tool cluster, and I need to specify the key that I use to set up the cluster. If I run this again, I'm connected to the master node, and now I'm on the master node of this HPC cluster. And on this master node, I have the queuing system, so I could say queue_stat, and there is nothing queued, which is good because there is nothing running right now. It's also using EFS, a shared file system that is spread across all the compute nodes. It's also having, well, the queuing system pre-installed. This is why I can say queue_stat. And yeah, that's it basically. And now I need something to run. And as you know, we always have these Hello World applications, and maybe the smallest Hello World application in MPI would be a small MPI program that is using message passing, but you know, not to simulate the climate for the next 100 years, but to do something really, really small. And I have something here. It's called Hello World MPI.c. It looks like this. It includes the MPI.h. It's a C program for those of you who haven't seen C for a while. And it's using all those MPI constructs, basically not doing much. It's getting a processor name, it's getting a rank. And these are the two things that I want to output here. So it basically says printf, processor name, rank, and the size. And then I say finalize, and that's the end of the MPI program. So all the thing that is happening here, this is not really what you need a HPC machine for, but that's the smallest possible hello world that I can run on such a HPC machine. And if you look at this, it's compiled already. So if I say file, hello world MPI, it's an executable file. I could actually run this locally. And it will say, well, that's the IP address. I'm rank 0 out of 1 processor. That's not the whole thing. No, this is not why I was talking about HPC. So what I want to do is I want to submit it as a batch job, and I want to make it run on more processors. This is why I have this MPI hello.sh. And if you look at this, it's a bash file. It's basically saying, well, load MPI, and then it's saying, run this on P equals 100 cores. So this is not what you can do locally. And I want to run this hello world MPI on 100 cores and then see the output. And that's what I do. I say qsub MPI hello.sh. Now it was submitted. If I say qstat, I see what is queued. Now this will take a little bit, not too long, but it needs to spread the program. It needs to be processed on 100 cores, and then it needs to collect the output. And what happens is there will be an output file. Now my ID was 10. That's the job ID. It's 10, and there is an output already. So if I say more MPI hello, the O10 is for my job number. Look at this. It says hello world from processor, and then it gives the IP address. It says rank. So MPI is ranking the internal processes, and this rank goes from 1 to 28 to 59. Why is that? Well, guys, it's parallel distributed. We don't have any synchronization. Then it goes on 2, 3, 5. That's okay. That's totally acceptable. This is what you need to understand if you write parallel distributed programs out of 100 processors. So it goes all the way down here, and this is the output. So I was running this on a 100-core machine. What you see now is that this 100-core machine basically consists of 2 physical machines, one with the IP address 2135 and one with the IP address 27220. And it's only those 2 IP addresses. So if I go to the console that you might know, let me make this a little bit smaller, you see them running here. And they were instantiated or spin up by the p cluster create command. Well, this is where I define it, and then the p cluster starts up the instances. So this is the C518X large. So this is basically what I was trying to show you. So to summarize, I strongly believe that having a fixed size, high performance computer that you lease for 4 or 5 years is not having that much of a future. We have a lot of customers, all different areas, from oil companies that do simulations for oil drilling to medical simulations to genomics. They all do high performance computing, and they all ask us to run these high performance jobs in the cloud. To run them successfully in the cloud, I think key is to have fast, low latency parallel networks, which is the FSX Lustre. The other thing that is even more critical, in my opinion, and that makes a real difference, is the networking, the EFA the elastic fabric adapter that you can just use if you want, and that gives you the low latency for the communication. Now, my program was just, spread across 100 cores and not doing any communication. But if you start doing simulations for climate, you have a lot of communication between those nodes, and then it counts how long it takes for every single communication. So we expect to see many, many more HPC applications on AWS, and that's why we invested for the parallel file system and the EFA, and also you've seen it yourself, we expect to see many more different instance types. There's a very famous speech, and I was doing this talk before, like 6 weeks ago. There's a very famous speech from an American president, not the current one, but John F. Kennedy, and he once said that there is a certain kind of problems, and we choose to address these problems not because they're easy and because we can solve them, but because they are hard. And he was talking about the mission to the moon, and HPC has many similarities now. It's also problems that we choose to address not because they're easy, but because they're hard. And the only thing that we can do to solve these problems is having good software, having good algorithms, first of all, but then also throwing massive amount of compute at these problems. That's the only way, to simulate the weather for the next 100 years. So HPC is one of them. And, I believe that the future of HPC will be in the cloud. This is all I had for today. I know we had a lot of competition from the Spring people next door. Thank you for being here. If you have any questions, I'll be around. Thanks. Do you have questions?
Hi, thanks for your...
You can ask them offline if you like. Oh, you got the microphone, cool.
Yes, thanks for the presentation. The question I have is it going to replace class replacement group?
I can't really hear you.
No?
No. Can we make it louder? Now I see you at least, yeah. Okay.
I'll come to you.
Just come here.
So, the question I have is it going to replace current placement cluster group, which we have in EC2?
The cluster placement groups?
Yes.
What is the question?
Is this technology presented today going to replace cluster placement group?
I don't know. I had to find out. That's the honest answer I can give you. Right now, I don't want to guess.
Okay, thanks.
Okay. All right. Thank you.